Hello, everybody. I hope you're doing well today. I thought we could take um, a look at something. Sadly, we're not going to get to do together, where we go outside with chalk and do our problems in an older school way, where we write them on the ground. Because of that I was doing it with many classes. This came in the form of rounds, and each round had 18 possible problems in case I had 18 groups of 2 in the class. So I'm going to do a sample from here. You might want to do more of them. I'm starting with round 1. These are pretty straightforward graphing rational problems. And let's take a look at problem number 2 from round 1. Problem number 2 says graph y equals 2x over x plus 4. I'm going to go through these quickly because I'm going to make the rash assumption that you watched the videos that led up to this and are comfortable graphing rationals. If you're not, you might want to stop this video and go back and watch those videos again. All right, so we see that 2x equals 0 means x equals 0 is our x-intercept. And when I cover up all the x's, I get 0 over 4. So I know my y-intercept is also 0. I see there's only one vertical asymptote at x equals -4. And my horizontal asymptote, because the degree of the top and the degree of the bottom are the same, I'm going to look at the ratio of leading coefficients. So y equals 2 is the horizontal asymptote. So we've got this vertical asymptote over here at -4. We're passing through the origin because of this, and a horizontal asymptote at y equals 2. So from this point, I'm going to bend to that asymptote and bend to that asymptote. But what about over here to the left of this vertical asymptote? Remember, there's something on each side of the vertical asymptote. And when I plug in a -5 here, I have -10 on top. -5 plus 4 is -1 on the bottom. So I have -10 divided by -1, which is +10. So my graph is up here at -5, 10. Okay, we know it can't be down here because we don't have any more x-intercepts. Okay, there's number 2. Let's take a look at number 4. Number 4 in round 1 says graph y equals 2x plus 3 over 5x minus 1. And again, this is pretty straightforward. My x-intercept will be -3/2. My y-intercept, when I cover up all the x's because I plugged 0 in for them, I've got 3 over -1. So that's a -3. Vertical asymptote at x equals 1/5, and horizontal asymptote y equals 2/5. Please don't make these so terribly, terribly close to the axes. Please give this room to see and to breathe. Here's x equals 1/5. Here's y equals 2/5. Now, I've got an x-intercept at -3/2, and I have a y-intercept at -3. So I'm going to connect the dots and bend to the asymptote. And then over here, I'm going to plug in a value like 1. I'm going to have +5 on the top and +4 on the bottom. 5 over 4. Well, that's more than 1, and that's less than 1. So I know my point is above the line. 1, 5/4. And we'll bend to the asymptotes there. Okie doke. All right, how about something a little more challenging? Let's take a look at problem number 5. The top has y equals x minus 1. The bottom, 10x squared minus 17x plus 3. You know, I feel like I better get right to factoring that bottom. 5x, 2x, 3, 1, minus. Now we've got an x minus 1 on top. Well, I notice there are no common factors, so there are no holes here. I don't have to worry about holes in this problem. I see an x-intercept at 1. I see a y-intercept. It's easier to see that over here, negative 1/3, when I plug zeros in for all those x's. I can see my vertical asymptotes here. Vertical asymptotes at 3/2 and 1/5. And my horizontal asymptote, because the degree here is 1 and the degree here is 2, my horizontal asymptote is y equals 0. So let's graph what we've got. We've got a vertical asymptote at 1/5, a vertical asymptote at 3/2. I've got a y-intercept of negative 1/3, an x-intercept of 1. Well, between these two numbers is 1.5. This is 0.20, so I'm going to go with here-ish for 1. Okay, and a horizontal asymptote here. So, yeah, this seems pretty straightforward over here. And then here, I'm just going to use a test point like 2. And rather than plug my 2 in here, I'm plugging my 2 into these factored forms. The numbers seem smaller and easier to work with to me, but certainly plug in over here. So 10 minus 1 is 9. 4 minus 3 is 1. 1 times 9 is 9 on the denominator. And what about up top? 2 minus 1 is 1. Well, there we go. We've got 2, 1/9. Because that value is positive, I'm up here with 2, 1/9. And my graph bends to the asymptotes. Now, what about here? Well, I could have a bunch of different things. Some students like to think we could have that, but I don't have an even multiplicity on this x-intercept. I didn't get this x-intercept twice, so I don't think I'm going to be seeing a bounce there. But maybe the negative x to the third, maybe the positive x to the third. And the only way I feel comfortable finding that is by plugging some test points in. So what's a number between 1/5 and 1? Well, I like 1/2. And what's a number between 1 and 1.5? I don't know. How about 1 1/4? So let's see what happens when we plug these in. If I plug in 1/2, 1/2 minus 1 is negative. And in the bottom, I plug a 1/2 here, I get 5/2. That's 2.5 minus 1 is 1.5, or 3/2. And then we're multiplying that by 1/2 times 2 is 1. 1 minus 3 is negative 2. And conveniently, this 2 and this 2 cancel. This negative and this negative cancel. And so I'm just going to do a flip and multiply, and I'm going to have 1/6. Since 1/6 is bigger than 0, I know my graph is doing that. So 1/2, and I believe that point is 1/6. So what about over here? Does it come down? Does it come back up? I won't know unless I test that point. That's 5/4. Okay, so I plug that in there. I have 25/4 minus 4/4 is 21/4. 21/4. And then over here, if I plug in 5/4, the 2 and the 4 cancel, and I have 5/2 minus 6/2, which is negative 1/2. We get negative, what about the top? I'm putting in 1 1/4 minus 1, and I get 1/4 or 1/4. So what am I looking at now? Well, I've got a negative on the bottom, I've got a positive on the top. That means my value is going to be negative. I probably want to, tidy this up. So I'm going to have 1/4, and then I'm going to flip and multiply 8 over negative 21. So those will cancel, and I have negative 2 over 21 at this point. Negative 5/4, negative 2 over 21. There we go. Okay. That's certainly, I think, the hardest we'll be experiencing. How about this problem, number 7, still from round 1. y equals x squared plus 2x plus 1 over x squared minus 4. Well, it's the same as x plus 1 times x plus 1 over x minus 2, x plus 2. So we know that we have vertical asymptotes of -2 and +2. We also have an x-intercept at 1. Oops, -1. Now, that is a bounce. That is x plus 1 squared. Huh, isn't that interesting? Well, let's see what happens when we plug in 0 for all the x's. I get -1/4. And if I plug in a number between -1 and -2, like -1.5, -1.5 plus 1 is -1/2, squared is 1/4. So I'm going to have 1/4 on top. And if I plug in that -3/2 in here, -3/2 squared is going to be 9/4 minus 16/4 is -7/4. If I flip and multiply, I get -1/7. Really? Yes, I do. Let's check again. Because a lot of students are going to want to do this. Yeah? But let's take a look. I plug in that -3/2. So -3/2 plus 1 squared on top. And I have -3/2 minus 4/2 times -3/2 plus 2. So up top, I've got -1.5 plus 1 is -1/2. I still need to square that. Oops, square that. And on the bottom, we have -7/2 times +1/2. Because this is 4/2 minus 3/2 is 1. So I get -7/4 on the bottom. And on the top, I have +1/4. And if I do that flip and multiply, sure enough, I'm going to end up with -1/7. So over here, -3/2, -1/7. And so we've got, okey doke. I know, kind of exciting. Horizontal asymptote at y equals 1. And what about over here? What about over here? Well, I don't have any more x-intercepts. So I'm pretty sure I'm going to be looking at this, and I'm going to be looking at this. But I definitely want you to label the test point here. Plug that 3 in. 3 plus 1 is 4. 4 squared is 16. And 3, well, that's 2. 3 minus 2 is 1. 3 plus 2 is 5. So I get 16/5. Now that's the same as 3 2/5. Well, if our y, our horizontal asymptote is 1, this number is definitely bigger than 1. So this point can be labeled 3, 16/5. Now over here, when I try -3, what changes because I plug in a -3? -3. Well, -3 plus 1 is 2. 2 squared is 4 on top. -3 minus 2 is -5. -3 plus 2 is -1. Negative times negative, +5. And that makes sense because that's also above y equals 1. But wait a minute, that's less than 1. Uh-oh. Let's go back and check work. So I'm plugging in a -3. -3 plus 1 is -2. -2 squared is +4. Yes. I plug in a -3 here. I have -5. And here, -3 plus 2 is -1. So -1 times 5 is negative. I'm wondering if I did it right yet again. -3, that's 9, that's +5. -3 is 9, minus 6, plus 1 is 4. But where is this? Negative 1/4. Y equals 1 because these degrees are the same, and I'm looking at the ratio of leading coefficients. But that's not bigger than 1. Whoa, what's up with that? Kind of want to pull out a calculator and look at this graph. Did I make some sort of big mistake somewhere? I don't know. You know, maybe I wonder if this is that case that comes down and back up. Wow, that'd be so mean of me. Oh, I'm not that mean. But I must be because I did that. Uh-oh. So yeah, I'm gonna open up a calculator. And I'm gonna take a quick look at this. Okay, so I'm graphing on top x plus 1, and we'd like that squared, thank you. No, not a comma. Okay. Clearly, I need to focus. So let's see what we got. Okay, we're putting parentheses x squared plus 2x plus 1, close parentheses, divided by parentheses x squared minus 4. Okay. And zoom 6. Huh. Okay, well, this definitely works. And we see this going down over here. But it's a little confusing what's happening over here. So I'm going to change my viewing window to go from -4 to 0 with these x's. Now, this one comes down. I see that here. And this one goes up. But let's go over to the table and plug in -3 and see what happens. Yeah, I get positive 0.8. But the horizontal asymptote is actually at 1. So this actually goes below the horizontal asymptote. Very tricksy. No, you don't have to worry about that. But it happens so rarely. I mean, look how surprised I am. Very, very rarely. In fact, I probably will take this problem out for next year. Okay. Feel like we should do 1 or 2 more. How about this one? This is number 8. Yeah, 8. So 8 says y equals x squared minus 6x plus 5 over x squared minus 16. Well, we want to factor these. X minus 5, x minus 1, x minus 4, x plus 4. So we've got 2 vertical asymptotes. One over here at 4, one over here at -4. We also see 2 x-intercepts. One here at 1, and one here at 5. The degrees are the same, so I look at the ratio of leading coefficients. And here's my y-intercept. -5 over 16. Excellent. Well, we know a lot of stuff here. I feel pretty comfortable making that part of the graph. And here, I feel pretty confident about that, but we could always plug in a 2, just to make sure there's no bounce like in the last problem. 2 minus 5 is -3. 2 minus 1 is 1. 2 minus 4 is -2. 2 plus 4 is 6. And I could take a 3 from each of those, and I end up with negative divided by negative, which is positive 1/4. So if I plug in a 2, I get 1/4. All right. Now, what about over here? Well, I don't have any x-intercepts, so I'm really at -5, expecting something up here. Let's just confirm. -5 minus 5 is -10. -5 minus 1 is -6. -5 minus 4 is 1. -5 plus 4 is -1. So I'm going to have 60 over negative 1, which is negative 60. Am I missing something? What? It's down here. Did I have another x-intercept? I only had 2. All right, gotta go back and check again. Negative 5 is to the left of negative 4. Negative 5 minus 5 is negative 10. Negative 5 minus 1 is negative 6. Negative 5 minus 4, negative 9. And then negative 5 plus 4 is negative 1. So I definitely have a positive here, 60 over 9. So this is going to be negative 5. And I could take a 3 out. So 20 thirds. Great. Excellent. All right. Well, there you go. There's number 8. So, yeah, these were the pretty straightforward ones. Let's move on to round 2. Round 2 is partial fraction decomposition. So how about x over x minus 3? This is problem number 1 in round 2, by the way. This is what I need to decompose, x minus 2. So because I have these non-repeated linear factors, I'm going to have something like this as my setup. Don't forget to multiply everywhere by the least common denominator. This is always the least common denominator. So x minus 3, x minus 2, x minus 3, x minus 2, x minus 3, x minus 2. Cancel, get x, cancel, get a times x minus 2, plus, cancel, b times x minus 3. I've got 2 magic numbers and 2 constants to find. So I think I'm going to use magic numbers for this one. When x equals 2, this turns to 0. 2 minus 3 is negative 1 times b is negative b. And I'm plugging a 2 in here. So that means that b is negative 2. Okay, what about a? Well, if x equals 3, 3 minus 3 is 0, so all of this goes away. 3 minus 2 is 1. 1 times a is a, and I'm plugging in a 3 over there. So my decomposition looks like 3 over x minus 3 plus negative 2 over x minus 2. You could, of course, bring this down. I don't, for a number of reasons. But either way would be fine on test or quiz for us. Okay, so that's sort of a basic reminder of type 1 problems. Well, let's see what else we've got here. How about something like this one? 9x plus 21 over x squared plus 2x minus 15. Okay, I'm not trying to graph it. I'm trying to do a partial fraction decomposition, which means I need to put constants over factors. So I have to factor here. I can factor on top, by the way, and pull out 3, be left with 3x plus 7. And on the bottom, my factors are x plus 5, x minus 3. So my setup, a over x plus 5 plus b over x minus 3. Okay. Actually, this isn't rational graphing, so I really don't need to do that factoring there. Sometimes, habits just form. Okay, so we're going to multiply everywhere by our least common denominator, which is x plus 5, x minus 3, and x plus 5, and x minus 3, and x plus 5 times x minus 3. These cancel, leaving me 9x plus 21 equals, these cancel, a x minus 3, and these cancel, leaving me plus b times x plus 5. Again, I only have 2 constants, and I have 2 magic numbers, so I'm just going to use magic numbers here. If I put a 3 in here, 3 minus 3 is 0, so all this goes away. 3 in here. 3 times 9 is 27, so I get 48. And 3 plus 5 is 8 times b. So if I divide both sides by 8, I find out that b equals 6. And if I use the magic number x equals negative 5, this will disappear. Negative 5 minus 3 is negative 8a. Negative 5 times 9 is negative 45. Negative 45 plus 21 is going to be negative 24. And if we divide both sides by negative 8, we get a equals 3. So my decomposition will be 3 over x plus 5 plus 6 over x minus 3. There's our partial fraction decomposition. Excellent. Nice. Just those sort of basic things. Maybe you should do a couple of these. Here, I'll stop nattering on and you do this one. 3x plus 5. This is number 11, by the way. 3x plus 5 over 2x squared minus 5x minus 3. Okay, please do the partial fraction decomposition for that. Come back when you're done. I hope you started by factoring the denominator. And 3x plus 5 on top. So my setup is going to be a over 2x plus 1, b over x minus 3. If I multiply everywhere by the least common denominator, 2x plus 1, x minus 3. 2x plus 1, x minus 3. 2x plus 1, x minus 3. So these cancel, and we're left with 3x plus 5 over there. And then our equal sign. This cancels that, leaving me an a, and this stuff over here, x minus 3. Now we have our plus sign and our b, but this cancels that, so we just have a 2x plus 1 there. Fabulous. Again, I think I can use magic numbers here because I have two constants to find, but two magic numbers to work with. If I make x equal to 3, this disappears, and I have 7b. If I plug a 3 in here, 9 plus 5 is 14. So b must equal 2. And if I make x equal to negative 1/2, when I plug that negative 1/2 in there, negative 1/2 times 2 is negative 1. Negative 1 plus 1 is 0. That all goes away. Negative 1/2 minus 6/2 is going to be negative 7/2. And if I plug in a negative 1/2 here, I have 3, negative 3/2 plus 10/2 is negative 7/2. Looks like a is going to be positive 1. So my decomposition then is 1 over 2x plus 1 plus 2 over x minus 3. Ta-da! And while we can't do the calculus on this expression, the calculus with this expression is wicked easy. All right, how about this one? Will you do this one? It's number 14. This is a case 2 problem. And you probably already knew that, or you don't know what case 2 is, in which case, don't worry about it. X plus 1 squared. So, will you please do the setup there? Stop when you're done with the setup and let's compare notes. Okay, so being in case 2, we've got to represent all the possible power options. So we put both of these down. If I multiply everywhere by the least common denominator, again, that's the least common denominator, not this times this. If you do this times this, you will probably go to a very, very sad place. And don't blame me, because I'm telling you not to. I'm telling you to use this always as your least common denominator. Squared and x plus 1 squared. Great, so we have some canceling. And we've got our 3x plus 5 then our equal sign. This takes one of those, a, x plus 1, and b, these cancel, and I just have b by itself. So here I only have one magic number, -1. If I make x equal to -1, I'm going to have -3 plus 5 is 2. -1 plus 1 is 0, and 0 times a, that's going away. So I just have b here. Okay, but I don't have any more magic numbers, so what am I supposed to do in this situation? Well, in this situation, what I'm supposed to do is choose a not-so-magic number, like x equals 1 or x equals 0. So if I plug a 0 in here, I've got 5 equals, if I plug in here a 0, 0 plus 1 is 1. 1 times a, and bring down that b. Well, we know that b is 2, so I can say a plus 2. And if I subtract 2 from both sides, I get 3. That's using a magic number and a not-so-magic number. What happens if instead we used systems? So with systems, I have to distribute ax plus a plus b. And here I want to group all the a stuff together. Divide by x. And so I get 3 equals a. Now I want to take all the stuff that doesn't have an x and write an equation. But wait, we know that a equals 3. And so when I subtract 3 from both sides, I get b equals 2. So 3 over x plus 1 plus 2 over x plus 1 squared. Ta-da! Done. Okay. Yeah, I think that can be enough of those. There's not a lot of variation after that. We'll go on to round 3 now. This means we're back to graphing. Yeah, what about this one? This is just round 3, number 1. This says y equals x plus 1 over x squared plus 1. Hey, any vertical asymptotes? Nope. No VA. At least no real ones for my graph. Y-intercept is 1. X-intercept, set the top equal to 0, I get an x-intercept of -1. And since the degree here is smaller than the degree here, we say y equals 0 for a horizontal asymptote. So what do we have? Well, I've got a y-intercept up here at 1, I have an x-intercept of -1, I have this horizontal asymptote. No vertical asymptotes here. Well, what's going to happen? Remember, we have to approach this asymptote as we head further and further away from the center of the graph. So I think I'm going to have something like this and something like this. Yeah, I don't know if this goes up and precipitously back down. I don't know if this goes through and very slowly back down. But we definitely want to convey the idea that we are approaching that asymptote. Okay, there's number 1. Maybe you should try one of these. Why don't you do number 3? Number 3 says y equals x plus 4 x squared. Oh, did I say 3? I did say 3. Yeah, 3 x squared plus 1. Okay, so what's it look like? I know it's very similar to the last one, isn't it? No vertical asymptotes, still y equals 0. 4 is the y-intercept, and -4 is the x-intercept. -4, there's 4, y equals 0. And so again, I think I'm doing something like this. You know, you can come down further if you wanted. There we go. In fact, I guess I could even have this one, you know, because our method right now, because we're trying to do this very quickly, that could also work. Most people put the max here and start coming down after that. But without calculus, we'd have to be pulling out a graphing calculator to figure this out. And I just don't quite want to get there. All right, What are we going to do with this one? Yeah, this one. Y equals x squared plus 3x minus 4 over x minus 1. Give that one a try and come back when you're done or have questions. We'll take a look at it. So if I factor the top, I've got x plus 4 and x minus 1. I also have an x minus 1 on the bottom. That means there's a hole at x equals 1. Okay? And this is the thing I'm supposed to graph. This is a linear function. It has a slope of 1 and a y-intercept of 4. -4, 4, and that's what I'm graphing. But at x equals 1, there's a hole. Okay? Okay. Nice. What about the slant asymptote? Yes, I agree. This degree is bigger than that. But let's see what happens when we try long division here. X squared plus 3x minus 4. What do I multiply this by to turn into that? Just an x. And when I subtract, 3 minus a minus 1, 4x minus 4. What do I multiply that to turn into that? A positive 4. And look, my slant asymptote and the leftover stuff that I'm supposed to graph are the same thing. And therefore, our graph sits on top of, exactly on top of, our slant asymptote in this case. This is all my graph. All right, how about number 8? Let's take a look at 8. 8 says y equals x squared minus 5x plus 6 and x squared minus 4. Okay, give this one a try. Can't wait to find out how it goes for you. So I hope you factored. A lot of students don't factor here, or they factor incorrectly. That has to be a minus. Okay, and on the bottom, x minus 2, x plus 2. So these are going to cancel. I've got a hole at x equals 2. I have a vertical asymptote at x equals negative 2. I have an x-intercept at 3, and my y-intercept is negative 3/2. So if I graph what I know, oh, and this is what I'm supposed to be graphing, right? And don't worry about this. That just creates the hole at 2. This is the stuff that is important to me. Like, look, there's my y-intercept of negative 1.5. Look, there's my x-intercept of 3. Nice. So let's graph what we've got. We've got an x-intercept at 3. We have a vertical asymptote over here at negative 2. We have a y-intercept here at negative 3/2. And, yeah, I got everything. So I think I've got something like this. No, not quite. Look at the degrees. They're both the same. So my horizontal asymptote is y equals 1. Okay. Is that all there is? No, silly. There's got to be something over here on the left side. So let's plug in a negative 3. You can plug it in here. You can plug it into all of this, but since those go away, I like plugging my negative 3 into here. So I'm going to have a negative 6 on top. And if I plug in a negative 3 here, negative 3 plus 2 is negative 1. Well, that's positive 6, which is bigger than 1. And so my point goes here, negative 3, positive 6. And then with confidence, I can have my graph approach those asymptotes. Okay, but are we done? Feels done, not done. What still needs to happen? That's right. We said there was a hole. Where's the hole? There's no hole here yet. Put the hole at 2. Now, the y value of this whole at x equals 2 is not 0. So I get upset when people put this whole on that x-axis. Let's take a 2 and plug it into each of these x's. 2 plus 2 is 4. 2 minus 3 is negative 1. And so I get a y value here of negative 1/4. That's not 0. So that limit, the limit of the y values there, not going to be 0 there. Don't force that. Okay. What's next? I kind of feel like I did that. How about you do this one? Let's break out room number 11. And breakout room number 11 says x squared. We're graphing this x squared minus 4 over x squared minus 5x minus 6, no, plus 6. Okay, give that one a try now. Hi, welcome back. I hope you factored. And then we can cancel and again say whole at x equals 2, vertical asymptote, x equals 3, x-intercept, negative 2, and the degrees on top and bottom are the same, so I'm looking at the ratio of leading coefficients. I'm saying horizontal asymptote at y equals 1 over 1 or y equals 1. Finally, the y-intercept, negative 4 divided by 6, reduces to negative 2/3. So let's graph what we know, a vertical asymptote over here at 3, an x-intercept over here at negative 2, a horizontal asymptote at y equals 1, a y-intercept of negative 2/3. Look at that, just waiting to be drawn. But what about over here? Well, I don't have any more x-intercepts, so I don't think it's going to be this piece. But let's plug in a test point so that people can be reassured, and sometimes that means us. 4 plus 2 is 6, 4 minus 3 is 1, 6 over 1 is 6. And 6 is in fact bigger than our y equals 1 horizontal asymptote. And so my graph is going to look like that. Nice, nice. Did we have a hole? Yeah. See, here's the thing. Unless you keep reminding yourself, you're going to forget to check. There's a hole at 2. Let's move that over a little bit. Yeah, we've got a hole at 2. Because so much good work, so nice a graph, but if you leave out the hole, I've got to mark it wrong. So please be mindful of that hole. Okay. One more, or are you good? I think you're kind of good with this. How about round 4, our last round with sidewalk chalk? Sorry you didn't get to do that. In round 4, I want to take a look at this one. Number 1. Number 1 says x squared plus 2x plus 7 over x minus 1 squared. All right, well now this is not graphing. This is a over x plus b over... Hey, why don't you finish writing the setup? You finish writing the setup, pause the video, come back when you're done. All right, so did you remember case 2? X minus 1 plus c x minus 1 squared. Remember, we have to represent all the possible power combinations. Not just that one, but yeah, that as well. And if this was a 3, then I'd have d over x minus 1 to the 3rd. We don't have that. We have a 2 there, so I'm stopping there. And again, I'm going to multiply everywhere by my least common denominator, which is not these things multiplied together, but rather this. X minus 1 squared, x minus 1 squared, x x minus 1 squared, and finally x minus 1 squared. So this takes out that, and that leaves us with x squared plus 2x plus 7, a x minus 1 squared, takes one of those, b x minus 1, and cx. Okay. Now what? Well, I've got two magic numbers, so, but I've got three constants to find. I don't know. Maybe it would be better if I did systems here. I'm not sure about that. Maybe we should do it both ways. Let's see. This is going to be ax squared minus 2ax plus a plus bx squared minus bx plus cx equals x squared plus 2x plus 7. Okay. So let's cx over there. Let's take all the x squared stuff and put it together. X squared equals ax squared plus bx squared. And if I divide everyone by x squared, I get 1 equals a plus b. Now I'll take the stuff that has just x to the first and combine it. And so now I've got 2x equals negative 2ax minus bx. Again, I can divide everywhere by x, and so now I have 2 equals negative 2a minus b. I still need to make the equation with the non-x stuff. 7 equals a. Oh. Whoa. That's some minus, good, but don't lose that. Plus cx plus c. Okay, so here then 7 equals a. Well, that's the only, yeah, I think that is accurate. That would be a bx. Okay, so I know a is 7. 7 plus b equals 6. Sounds like b is negative 6. And if I plug in a 7 here, I have negative 14 minus a minus 6 plus c equals 2. So I have 16 equals 6 plus c, or 10 equals c. So we have our values, and we can go back to our original problem setup and put in a 7 here, and a negative 6 here, and a 10 here. Because remember, this was my A, my B, my C. Nice. Well, that was longer than some of the ones we've done, but it wasn't very hard. I just had to take my time with it. How about you do breakout room number 3 in round 4, which says 3. Did I say number 3? No, I'm not looking at number 3. I'm looking at number 5. Okay. Which is 3x plus 16 on top, and x plus 1, x minus 2 squared on the bottom. So give that one a try. Remember, we're not graphing. We're doing partial fraction decomposition. Okay. So our setup, a over x plus 1 plus b, x minus 2, c, x minus 2 squared. And I'm going to multiply everywhere by my least common denominator, x plus 1, x minus 2 squared. All right, so what cancels? Well, you can see that all this cancels all this, leaving us 3x plus 16. Then our equal sign. This takes that, so we have a x minus 2 squared plus one of those, b x plus 1, x minus 2. This takes all of those, leaving me just c x plus 1. Okay, so the last one like this I did with systems. I think we're going to use magic numbers here. X equals 2. 6 plus 16 is 22. 2 minus 2 is 0. That goes away. 2 minus 2 is 0. That goes away. 2 plus 1 is 3c. Ah, why can't that be a 21? Just going to check. 6 plus 16, no, 22. 3, 3, done. I have a c value. Now, what if x is equal to negative 1? Well, over here, negative 3 plus 16 is 13. Here, negative 1 minus 2 is negative 3. Negative 3 squared is 9. Negative 1 turns this into 0. Negative 1 turns this into 0. So that's, yeah, I'm just going to have, hold that thought a second. I was plugging in negative 1. I lost the a. 9, a. And then I plugged in a negative 1 and these went away. Okay, so then 13 ninths is our a value. All right. We need a c. No, that's a c. We need a b still. And at this point, I need a not so magic number. I've used negative 1 and positive 2. How about 3? 3 minus 2 is going to be 1, and 1 squared is pretty easy. Over here, I have 9 plus 16, or 25. My equal sign, 3 minus 2 is 1. 1 squared times a is 1a. If I plug a 3 in here, 3 plus 1 is 4, but 3 minus 2 is 1, so I'm just going to have 4b. And then here I'm plugging in a 3, and I get 4c. So what do we know? Well, we know a, and we know c, and we can plug these in here and solve for b. Okay? So, yeah, this is ninths. So I'm going to make this ninths as well. So I'm going to have 4 times 66 ninths, 4b, and then here I just have a, so 13 ninths. And how many ninths is this? This is 225 ninths. So what do we have going on here? 264, I think. 4 times 66. Yeah, 264 over 9 here. Plus 13 is 277. So I'm going to subtract 277 from 225. And I get negative 52. So what I note then is 4b equals negative 52 over 9. And if I divide both sides by 4, I notice that 4 goes into 4, and 4 goes into negative 52, negative 13 times. So my b value is negative 13 ninths, my a value is positive 13 ninths, and my c value is 22 thirds. Okay, that seemed doable. Don't forget when you're done finding these constants to actually plug them back in. 13 ninths over x plus 1 plus negative 13 ninths over x minus 2, and finally 22 thirds over x minus 2 squared. Okay, that's my answer. What else do we need to look at here? Ooh, how about breakout 7? Have you been thinking about case 3? 5x squared minus 6x plus 7 over x minus 1, x squared plus 1. This is an irreducible quadratic. So my setup, a over x minus 1, but this, I need 1 degree less. So I'm going to need a bx plus c over that x squared plus 1. If that's second degree, that's got to be first degree. The only thing to watch out for is if I have this, x minus 1 squared. Yeah, I'm good with that. I'm even good with that. This squaring is on the outside. That squaring is on the outside of x, but on the inside of this transformed point. So why does that make a difference? Well, notice here, x squared becomes x to the first on top. But here, if I FOIL this out, I have x squared minus 2x plus 1, but that doesn't affect this in the same way I see here, that value being bringing about some sort of change. In particular here, the change we're talking about is we want 1 degree less here than we have here, and that looks to some students like the same situation. It isn't. Yeah, no, this is case 2. With case 2, we're looking at that. The thing in the parentheses is what determines the setup. All right, well, I sort of feel like, all right, well, we'll just do this one. Finish this one off, and we'll call it a video. So I'm multiplying everywhere by my least common denominator, x minus 1, x squared plus 1, x minus 1, x squared plus 1, x minus 1, x squared plus 1. And so what cancel? This with this, 5x squared minus 6x plus 7. This with that, a x plus 1, don't forget the squaring. And here, to be very careful, I have to end up with that sort of binomial situation there. Okay, distribute, FOIL. Do I have to? Well, I've got one magic number. I've got another magic number. I have 3 constants. You know, this is one where it could go either way. I think I'm going to go with magic numbers today. I'm going to start with x equals 1. So 5 minus 6 is -1. -1 plus 7 is 6. If I plug a 1 in here, I get 2a. If I plug a 1 in here, I get b plus c times, I plug a 1 in here, I get 0. So I might not have to worry so much about that. That's nice. A equals 3. And I mentioned another magic number. That other magic number is 0. That's going to make b disappear. And these things here, leaving me just that 7. So I get 7 equals 0 plus 1 is 1a plus, I plugged in a 0 here, b goes away, plugged in the 0 here, and so I end up with minus c. Is that really a minus c? A. I put in the 0 for x, so I'm just looking at that. -1. Yep. Oh, but I know what a is. So minus c equals 4, and c equals -4. But for all that work, we don't have all 3 constants solved for. We need one more. We need a not-so-magic number. How about x equals 2? I like 2 because 2 minus 1 is 1. 4 times 5 is 20. 20 minus 12 is 8. 8 plus 7 is 15. And then over here, 2 squared is 4. 4 plus 1 is 5a. Plus 2 minus 1 is 1. Nice. So just distribute the 1 there. Uh, so I'm going to have bx plus c. Okay. We know c is -4. We know a is +3. And so I end up with 4 equals bx. And so I get b equals 4. All right, well, that's going to be our video today. I look forward to hearing from you in the near future.